Welcome in Dark Core. Dark matter makes up about 80% of the universe's mass. Yet, its origins remain one of the greatest mysteries in science. While its presence is confirmed through its gravitational effects on galaxies and large-scale structures, the question of what it is has eluded physicists for decades. Recently, two intriguing theories have emerged proposing that it could have naturally formed in the early universe. These theories, based on established physics, suggest that it might have emerged from a hidden mirror world or through quantum radiation near the universe's cosmic horizon. In this video, we will explore these theories and their implication for our understanding of dark matter. Mirror world hypothesis, one of the theories published in July 2025, introduces the concept of a mirror world. This theory suggests the existence of a hidden sector, a mirror universe that runs parallel to our own. While this universe would follow the same fundamental physical laws, its particles and forces would be entirely separate from those we observe in our universe. Essentially, this hidden universe would be invisible to us. Yet, its particles could have a profound impact on the cosmos. The theory builds on quantum chromodynamics, QCD, the theory that describes how quarks are held together inside protons and neutrons by the strong nuclear force. In the mirror world, particles known as dark quarks and dark gluons could form dark baryons, which are composite particles similar to protons and neutrons. Under certain conditions in the early universe, these dark baryons might collapse into small, stable black hole-like objects. These objects would behave like black holes, but would be invisible to traditional particle detectors, since they would not emit light or interact with electromagnetic radiation. The key idea here is that these dark objects would only interact through gravity. While they would be undetectable through conventional means, their gravitational influence could explain the effects we see in the universe, like the rotation of galaxies and the movement of galaxy clusters. This could account for the dark matter that binds galaxies together while leaving no trace of its existence in terms of detectable particles. What's compelling about this theory is that it offers a testable framework based on quantum chromodynamics, providing a clear, calculable path for future experiments to verify or challenge its predictions. Cosmic horizon radiation theory, the second theory published in May 2025, offers a completely different explanation. Dark matter might have been produced by the universe's cosmic horizon. Similar to how black holes have an event horizon, the universe has a boundary called the cosmic horizon. This marks a limit beyond which we can no longer observe because space-time is expanding at an accelerating rate. This theory suggests that during a brief period of accelerated expansion less extreme than the rapid inflationary phase that followed the Big Bang, quantum effects near the cosmic horizon could have generated particles. These particles would have been created gravitationally, not through any direct interaction with ordinary matter. Essentially, the universe's expansion through quantum radiation near the cosmic horizon could have led to the formation of stable gravitationally bound particles which we observe today as dark matter. The key advantage of this theory is that it does not rely on any assumptions about new exotic particles. Instead, it proposes that it naturally emerged from the conditions present in the early universe. The particles produced by this mechanism will be stable and interact only through gravity, meaning they could influence cosmic structures without interacting with light or electromagnetic radiation. This model builds on quantum field theory and curved spacetime, a framework that is already well established in physics. It offers an elegant solution by explaining dark matter's formation during the early universe without invoking unknown particles or forces. While still speculative, this theory presents a clear and calculable framework for future research and experiments. Implications and challenges: both theories offer plausible, testable scenarios that could explain the origins of dark matter, challenging traditional particle-based models. They provide clear predictions based on well-understood principles such as quantum chromodynamics and quantum field theory that can be tested through future observations and experiments. These theories could provide much-needed alternatives to existing IT models such as those based on weakly interacting massive particles, WIMPs, which have struggled to produce experimental evidence. One of the most compelling aspects of these theories is that they do not rely on the discovery of exotic particles or new forces. Instead, they suggest that it could have naturally emerged from processes we already understand, such as gravitational effects and quantum mechanics. This makes them much more grounded in established science and provides a promising avenue for future research. However, both theories face significant challenges. The mirror world theory proposes that dark matter objects interact only through gravity, making them undetectable by traditional methods. While their gravitational influence could be measured, detecting these objects directly would be incredibly difficult. Similarly, the cosmic horizon radiation theory depends on a specific period of accelerated expansion in the early universe, and validating this mechanism through observation could be challenging. Despite these challenges, the potential of these theories to explain it in a way that is consistent with current physics is exciting. They offer new insights into how we might think about it, moving beyond particle-based models and opening up new research directions. Testing these theories will require novel experimental techniques and observational methods, but it could ultimately provide a breakthrough in understanding one of the universe's greatest mysteries. Outro Professor Stefano Profumo's theories offer new perspectives on dark matter, suggesting a mirror world or the cosmic horizon's role in its creation. These testable models challenge traditional particle-based theories and could lead to breakthroughs in our understanding. As technology improves, we may soon test these ideas more rigorously, potentially reshaping our view of the universe. The search for dark matter remains one of physics' most exciting frontiers. Stay tuned as scientists uncover its secrets. Thanks for watching Dark Core.